morning. In the last class we looked at the solution for the dispersion equation, namely we called it as the diffusion equation, and we found that the solution to the diffusion equation was given by something like the concentration at any distance away from the source, wherein at the source you have a concentration, let us say Ci, let us say kilograms per meter cube, at a distance x from the source and at a time t away, and at a time t from the time that the source releases its particular concentration, well, the concentration C is equal to Ci into exponential of minus of the distance divided by under root of time, and we also had it multiplied by the diffusion coefficient, that means under root 2t, and the whole thing was minus x by 2 under root dt whole square. Now, we looked at this particular equation which we solved for the concentration at any distance x at time t, and we found, well, this equation is somewhat similar. It has the decaying characteristics of something like a Gaussian distribution, and we also found, well, if I have something like a distribution, let us say the distribution function divided by p as given by p is the distribution function p is given by 1 over under root 2 pi into the standard deviation into exponential of minus a dummy variable w divided by 2 into the standard deviation square. Now this is the standard distribution function, and the standard distribution function which we always say is Gaussian is such that the area under the distribution function under the entire area from minus infinity to infinity is equal to 1. What does this signify? Let us say I have a distribution function which is sort of peaked over here, shown by the black line. All which shows is maybe it is peaked, I have a standard deviation which is minus sigma on the left hand side plus sigma, the standard deviation is sigma. The area under this whole curve starting from here to here is 1. If I have a distribution which is sort of distributed, the peak comes down, like for instance the concentration sort of diffuses out, then what happens is that the diffusion is scattered. In other words, the standard deviation increases, but still the area from minus infinity to infinity is equal to 1, and this is what a probabilistic distribution function gives you. Now, when I look at the value of the concentration as a function of distance, as a function of t, I find if I can substitute, let us say under root dt by, let us say sigma, or rather we said, well, if sigma squared is equal to, let us say dt, then I can write this particular concentration as, let us say, the mass release at the particular source divided by under root 2 pi into the standard deviation into exponential of minus x squared by 2 sigma square. Rather, this particular diffusion equation which gives the concentration at a distance x at time t is somewhat similar to the Gaussian distribution function. Further, the distribution of the concentration taken from minus infinity to infinity, namely Cx dx from minus infinity to infinity is equal to q, and this is somewhat similar to this. Therefore, we said, instead of solving for this particular equation, and why we are scared to solve this equation in terms of d is the diffusion coefficient d, which was given in meter square per second. It's a function of let us say the turbulence, the medium, the wind velocities, the gust velocities, and it's very difficult to have a assessment of d and numerically solve this equation. Even in 1D it is difficult, and therefore, because the value of d depends on a host of parameters, but we found when we described the atmosphere, we were able to describe the atmosphere as saying atmosphere is unstable, atmosphere is stable. Therefore, we could get the experimentally the standard deviations from based on experiments, and then use this type of equation to be able to solve our problem. And having decided how to go about it, let us go to the next one. Here we see, well, I write this equation again. We said, well, the concentration at any distance x can now be written as, if I substitute dt as equal to sigma square, I have the mass which is released at the source divided by 2 pi sigma exponential of minus x square, and over the entire range, because I am talking of one dimension from minus infinity to infinity, the concentration when integrated gives me the mass over here. Now this is in one dimension, but a diffusion does not occur in one dimension. It could occur along the x direction, it could occur along the z direction, it could occur along the y direction, and therefore for a general problem, if I were to write my concentration as chi, and we said unit of concentration is kilogram per meter cube, that is what we considered since the mass release at the source is q kilograms, I can write chi as a function of x, y, z. All what I say is, well, q is released, I have under root 2 pi sigma x corresponding to the x direction, I have under root 2 pi sigma y, that means I multiplied by 2 pi into sigma y, under root 2 pi sigma z, and therefore I get 2 pi to the power 3 by 2 into sigma x into sigma y into sigma z into exponential. This was one term, minus x squared by 2 sigma square. I have now the diffusion taking place in y, that is in the lateral direction, or let us say this is the x direction, in the y direction I have diffusion taking place. Therefore along y I have the diffusion coefficient sigma y over here, which is the standard deviation in the y direction. I also have z square corresponding to the vertical direction 2 sigma z square. Well, this is what the value of concentration should be. Therefore, if I can determine experimentally the value of the standard deviation sigma x, the standard deviation sigma y, the standard deviation sigma z, well, I can determine the concentration at any location x, y, z, and of course the constraint comes from this, and this constraint was in one dimension. If I were to put it in all the three dimensions, well, I write concentration now as chi x, y, z at any point. I integrate out along the x direction from minus infinity to infinity, in the y direction from minus infinity to plus infinity, dz along this, and this gives me the total mass. Therefore, this is the final form of my dispersion relation, in which now if I can take into account the atmospheric stability and get the value of sigma x, sigma y, sigma z, I can find out the concentration at any x, y, z for the particular mass q at a given point, and this is what we will be doing today. That means in this case I am considering q to be released at q kilograms of the substance or of the particular vapor or of the particular gas to be released at a point. Having said that, well, I further illustrate this over here. Let us say I have something like a spill which is in the form of a puff. That means all of a sudden I release q kilogram of, let us say, a gaseous mixture at this particular point at time t is equal to 0. What is going to happen? I release it at t is equal to 0. What is going to happen when I release a substance over here? Well, the substance diffuses out, it increases its volume, and as the volume of the substance increases, the concentration, which was originally quite high, will keep on decreasing as the time progresses. Rather, this is at time t is equal to 0. When I look at it, maybe at x increasing, y increasing, z increasing, the volume increases, and this is where I say, well, the volume has increased. Therefore, if I have something like a release of q kg at time t is equal to 0, I call it as something like a puff, just something released at time t is equal to 0. With subsequent times, well, the puff or the mass which is released in the puff keeps on increasing its volume. And how does it increase in volume? Well, we said q divided by 2 pi to the power 3 by 2 sigma x, sigma y, sigma z into exponential of minus x squared by 2, the standard deviation x square minus y squared 2 sigma square, into we had minus z squared by 2 sigma z squared. If you look at the previous expression over here, we had z squared by 2 sigma z squared. But in case the puff is released, let us say at a height h from the bottom, let us say I have the ground over here, the puff is released at a height h, like from a chimney I have a burst of mass which is coming out, let us say, or a balloon at a height releasing a certain mass. Then what is going to happen? This particular mass which is released, the distance I am interested is z, therefore z minus h is the distance above, therefore I have corresponding to minus z squared by 2 sigma z squared. I have z minus h squared divided by 2 sigma z squared, but a part of the burst also, or the mass, comes down to the ground, gets reflected on the ground. That means I have h coming over here, h coming over here, 2h plus z minus h gives me z plus h, and therefore I have another term due to the reflected one. And therefore, whenever I have, let us say, a puff or a mass which is released at a height h above the ground, the concentration of at any x, y, z point is given by this particular expression, namely q divided by 2 pi to the power 3 by 2, the standard deviation in the x direction, standard deviation in the y direction, standard deviation in the z direction, into exponential of minus x squared by 2 sigma x squared minus y squared by 2 sigma y squared into exponential of the forward term and the reflected term from the particular ground. Well, this is how we calculate. We will do 1 or 2 model problems after looking at different types of releases. In this case, it is a puff over here. Let's consider some other release. We said, well, I release some mass, well, it diffuses out in this particular direction. I could also think, instead of just releasing a mass q, supposing I have certain leak which takes place on the ground. Let's consider the case of, let's say, Port Hudson leak. Let me go to the board and explain what I am trying to do. Well, I have the pipeline which is containing liquid propane. The pipeline, let's say, bursts, and therefore I have liquid propane which gushes up. When the liquid propane comes, well, it is at the ambient temperature corresponding to the high pressure here, but then its boiling point under the ambient condition is something like minus 45, but the ambient temperature is higher over here, therefore it flashes into vapor. Therefore, you have the leak taking place, and the leak does not take place at 0 time. It keeps on leaking, considering the amount of fluid in the pipeline, and the fluid is pumped by a station which is quite a distance away from where the leak is happening. You have a constant source of leak. That means I am always having something like m dot, or in this case I would call it as q dot, which is taking place over a considerable period of time. That means the amount of leak is so much kilogram per second, and it occurs steadily, let's say for a period of 2 minutes, or maybe if the leak is prolonged, it could happen for a period of an hour. Therefore, we want to find out, if I have something like a steady leak like this, steady leak taking place, what is the effect, what is the concentration, let's say at a distance from over here, at a distance x over here, maybe at a distance y, and maybe above the ground at a distance z is what we want to calculate. Therefore, when we talk of the steady leaks, it is something like, let's say, a chimney, in which the gas is continually flowing, something like I have an m dot s so much kilograms per second. Instead of talking in terms of m dot s, I talk in terms of q dot. Let's also say it's a steady leak. Let's say q dot s so much kilograms per second is being spilled. Therefore, in the problem, what I want to consider is, let me get back to the slide. I have something like q dot s kilograms per second, which is coming out over here, maybe from a pipeline rupture or a leak which is a steady leak. And what is happening? If I have a wind condition, see, yesterday or in the last class, we also considered the effect of wind. We said wind will affect the stability of the atmosphere, and always, even when it is summer, we have some small wind, let's say 1.5 to 2 meters per second. Sometimes we have heavy wind. The wind, what it does is, when something is leaking, it tends to carry the leak along in the form of a plume. By plume I mean, the shape of the shape of the substance which is getting leaked out. That means the concentration of the particular substance which leaks out expands out in the form of a plume over here. Therefore, when I talk of steady release, namely Qs kg per second, I am looking at this particular plume, and this particular plume is carried by the particular wind velocity. Just like I had an equation for a puff, I would like to have an equation for the steady release which takes place due to a consistent leak. It is not just once I release a mass and keep quiet, but a leak continues for quite some time. Therefore, to do this problem, Well, I have to again focus on the coordinate system. Well, I have maybe the height at which the leak occurs is given by the small h value, and because there is a particular velocity with which the leaking gases are propelled forward, well, it comes forward, it reaches an effective height h, and over here the effect of the initial velocity is lost. That means I am considering a gas whose molecular mass is near to the molecular mass of air. It is being released, it has an initial momentum, it comes to an effective height h, and when it reaches an effective height h, well, the wind takes it off, and if the direction of the wind is in a particular direction, let us say x direction, you know, the wind takes the plume or the leak gases away, and what happens is when the wind is taking it away, let us say in the x direction, I show the wind direction is x, I have the lateral direction over here, which is the y direction. Along the y direction, maybe initially along the center line over here I have maximum concentration, and along the lateral direction, well, the mass diffuses out or disperses out, therefore the concentration is maximum along the center line, and then the concentration decreases along the negative y direction, decreases along the positive y direction, and if it still further increases, well, the concentration further diffuses like this, further it diffuses, the center line concentration diffuses, and the concentration along the lateral direction diffuses. Similarly, you know, when the concentration is released over here and the wind is taking it forward in this particular direction, maybe in the vertical direction also, you know, in the vertical direction, well, the mass is released over here, in the direction downward, well, the concentration is lower, at the center line, well, the concentration is maximum, well, above it, well, the concentration decreases, and you have something like a Gaussian distribution here. As the steady release progresses forward, well, the concentration becomes something like this, well, it becomes even shallower like this, that means the standard deviation keeps increasing, and this is how a steady release changes its distribution in the lateral direction, changes its distribution in the vertical direction, but along the wind direction, well, it is just carried forward by the wind. Therefore, there is not much of a distribution because we are talking of the direction along the wind. Let me clarify it through another figure over here. Well, I have the height of my release, which is a steady state release corresponding to q s dot over here. You know what happens, the initial movement pushes it over here, this is somewhat a point at which it has lost its initial momentum, and at this point, well, the wind is taking it forward, the wind is taking the release q dot s forward, and along the lateral direction, well, I have the distribution at the center line, I have maximum, at the edges I have this. If I look at a vertical, if I take a section over here, well, I have the vertical along the center line, well, I have the maximum concentration. If I go further and further in the vertical direction, the concentration decreases, I have a distribution in the vertical direction. Therefore, I show in this particular figure the x direction along the wind, the y is the lateral direction, and well, z is the vertical direction. I am interested in finding out the concentration at any distance. Let us say this is my release over here, I am interested at x, y, z, or I am interested at this x, y, z. And how do we do this problem now? See, we know how to do a problem for a puff. I want to do it for a case of a steady plume. Therefore, first we recognize, well, the wind is taking the concentration chi, and we said concentration units at any distance, let us say x, y, z, we said is chi, which is equal to kilogram per meter cube, chi into the velocity into dy into dz. Well, this is kilogram per meter cube, this is meter per second, this is meter, this gives me kilogram per second, and therefore, if I integrate out this particular mass, the plume which is travelling forward from, let us say, at this particular point being, let us say, 0, which corresponds to infinity, because in this direction I have nothing, the wind is taking it forward. I integrate from, let us say, the y going from minus infinity to infinity. Let us, for instance, consider a particular section over here. at this particular section, well, what is the mass which is going across the section? Well, the mass which is going is chi u dy into dz at this particular section. Therefore, I want to integrate let us say lateral to this section, and lateral to this section is along y. Therefore, dy going from minus infinity to infinity, and then I take vertical, that is in the direction, let us say vertical to the center line, vertical to this one, going from minus infinity to infinity, and therefore, I integrate from in the lateral direction, I integrate in the vertical direction, and therefore, I have a relation chi into u into dy by dz is equal to q dot s, and therefore, if I now assume that the wind speed is a constant, mind you, I will go and examine whether the wind speed can really be constant or not. If the wind speed u meters per second is a constant, well, I can take it outside, and therefore, I have chi into dy by dz is equal to q dot s by u. Therefore, now I have the value of q dot s by u, and if I now plug this equation into the standard equation by which I have been looking at the particular mass getting diffused, what is it I get? I get q dot s divided by u is corresponding to the mass corresponding to a particular value of x over here, and therefore, if I want to find out what is the dispersion taking place along the lateral direction y, along the vertical direction z, then I get q dot s divided by root 2 pi into sigma y into root 2 pi into sigma z. Now the mass I am considering is q dot s divided by u into exponential of minus y square into 2 sigma y squared, that is the standard deviation in the y direction, minus z squared by 2 sigma z square, and well, this is my concentration, because root 2 pi into root 2 pi gives me 2 pi u into this, and this is the way the wind carries the concentration along the particular x axis. That means wind carries q dot s by u, and I am looking at the dispersion in the y direction and in the vertical direction. Well, this is the formula therefore for concentration for a steady release. And if now I consider another aspect, namely I consider, well, you have a vertical height at which you have a steady release like a chimney. Let us consider this example again on the board. Let us consider, let us say, a chimney, and we have seen this, like for instance, whenever we take a power plant or something, you have this chimney, and what does this chimney do? It produces smoke, and there is a wind. Therefore, how does the smoke travel? Well, the smoke travels like this. This is the way the smoke travels from a particular chimney. Well, I have the height of the chimney is h. Well, immediately the thing does not traverse, and what happens in practice is, because I have the initial velocity over here, well, the little bit of smoke comes out like this, and thereafter it begins to traverse over here. Therefore, this is what I call as the effective height of the chimney, because the initial momentum pushes the dispersion from this point to the point shown by the violet line over here, and therefore, this is that type of dispersion what we get. Well, the ground is over here, and therefore, now if I am interested in my wind direction is x along this, well, I consider the lateral direction y. Therefore, this could be my lateral direction y, and this could be my z in the vertical direction. Therefore, I have something like this, and something vertical over here. Therefore, I am looking at the release q dot s divided by root 2 pi of sigma x. Rather, dispersion is along y. The mass is carried along u direction by the particular wind. Therefore, I have 2 sigma y into 2 pi into sigma z, and of course, you have the value corresponding to the exponential term coming as minus, I have corresponding to y square into sigma y square. I also have maybe the value of z square corresponding to sigma z square, and this gives me the value of the concentration at x, y and z. Along x, well, the wind carries it forward. Along y and z, well, the standard deviation, that means I have the distribution like this. After some time, well, it comes out like this. still after some time, well, it diffuses forward. Well, it comes like this and it diffuses forward, and the concentration along the center line decreases, and also the concentration along the lateral line also changes. This is the type of model we have. But if I have something like an effective height is what I showed there, h over here, I again get, just like in the case of a puff, I have the one which is forward, the one which is reflected, and therefore, when I have dispersion at a point x, y, z from a release which takes place at a height h above the ground, the value is q dot s divided by 2 pi u divided by 1 over standard deviation y corresponding to y, and corresponding to the z term over here, I get the forward thing which corresponded to z square, namely now my chimney or my height of the release is h, I have z minus h instead of z, and I also get the reflected one goes by h, comes back by h, 2h by z minus h plus 2h is z plus h, and this is the reflected one from the ground. And this is how we calculate the different values, and all what we have done is we have shifted the problem from trying to solve the diffusion equation to trying to find out what is the value of the standard deviation y, standard deviation z, and these are all experimentally determined and can be determined quite well, and tables are available. I will come back to this. And if I were to still focus back on the particular problem, well, this is the height, this is the value of concentration at x, y, z when the height of release of the particular steady value of the leak is, let us say, q dot s. It is given by this. If I am interested along the center line, that means for y is equal to 0, and on the surface of the ground, namely z is equal to 0, and what is it I do? I substitute y is equal to 0, in which case this factor becomes 1. I substitute z is equal to 0, in which case I get minus half h squared by sigma z square, plus I get z is equal to 0 plus exponential of half into z plus h, that means 0, that means exponential of h squared by sigma z. This gives me 2 times the exponential of h squared by sigma z square, and the expression now becomes the first term, the q dot s divided by pi u sigma y sigma z into exponential of minus h squared by 2 sigma square. And what is the difference from the previous one? Let's go back. You know what is happening? You know, we had z square, and you had 2 over here, and therefore 2 with 2 got cancelled. I had qs by pi u into sigma y sigma z, and therefore the concentration at any x as it disperses on the surface of the ground along the center line of the wind, that is on the surface of the ground along the center line of the wind as the mass diffuses out, is given by this particular expression. See, why is it we do not get a sigma s term? Because the wind is taking it forward, therefore no sigma x is required. But in practice, whenever we measure the value of the standard deviation sigma y sigma z, you know what happens is we measure it over a period of time, something like 10 minutes to an hour. And if I want the local concentration, you know, the local concentration could be little bit higher, and therefore the practice is, instead of having qs dot divided by pi u sigma y sigma z preceding the dispersion in the vertical direction, you multiply it by 2 to take care of this particular factor, and this is how we estimate the concentration. Well, we will do a problem, but before I do a problem, you know, we must be clear, how do we get the value of sigma y and sigma z for a steady release? See, we have already done something earlier, and let us see what did we do in the last class. We discussed about the diffusion or the dispersion of gases, and what did we tell? Well, atmosphere is not that easy to handle. We said, well, atmosphere could either be very unstable. When we say unstable, we meant that the temperature above the surface of the earth decreased. We also said, well, there could be an inversion, atmosphere could be stable. Well, the atmosphere could be very, very unstable. We said it is A, that is Pascal's classification. atmosphere could be very stable, like we have a very cold night and there is no wind at all, and therefore, nothing really leaves the earth, which is extremely stable, we called it as F. And in between A and F, we had B, which was unstable, C, B was moderately stable, moderately unstable, I am sorry, C was moderately unstable again, or weakly unstable. Then we had D, which was weakly stable, we had E, which was moderately stable, and F was strongly stable. Therefore, we had classification like A, B, C, D, E and F. And therefore, we would like to see how the atmospheric stability criterion under conditions A to F will include the value of sigma y and sigma z. Well, experiments are done, and what we get is plots of sigma y as a function of x. And what is it you observe? Well, when the condition is very unstable, well, it diffuses very fast because of the unstable nature. Well, A could be somewhere over here. Well, for the condition F, well, the condition F could be somewhere over here, because it is not able, the atmosphere is stable, it is not able to diffuse out, it comes back to the original point. And in between these two lines, we have for the different conditions, well, I could have maybe B over here, maybe I could have E over here, I could have the other line for, let us say, C over here, I could have a line for D over here, and corresponding to the atmospheric conditions, for when the spill goes over a distance, let us say x, the wind shifts it from here to here, I can find out what my values of these standard deviations are, and these standard deviations sigma y, sigma z are known as dispersion coefficients. We determine the coefficient sigma y, and similarly we also determine the sigma z values, and these are available both as plots and as equations. That means, in the downwind direction, well, sigma z could be here for the condition A, for the condition F it could be over here, it is not at all increasing, it is a small number, maybe for B, for C, for D, for E, these are the different values. And as we go from F stable to the unstable condition, well, the dispersion coefficient increases both in the sigma y and sigma z. When we consider a steady case, we do not consider sigma x, but when we consider a particular puff, we also consider the value of sigma x, and normally for a puff we will have the value of sigma x is equal to sigma y, because it travels in the same direction, because there is no wind, we are not considering the wind condition. We will also consider the case of a puff with wind shortly, but when there is no wind, well, sigma x is equal to sigma y, and this is how we calculate the dispersion coefficients. Now, there is one problem though, like for instance, all of us are used to living in an urban environment, that means in a city, whereas in a village which we call as a rural setting, well, the conditions could be different. In a village, everything is open, you have open area. In a city, you have a lot of these tall buildings which are available, maybe small buildings, tall buildings, roads, vehicles, all these things are more in an urban area compared to the rural area. Therefore, what would happen if there is a spill, or if there is a, let us say, a steady release in an urban area, it means more of these resistances due to the buildings and all that. Well, some eddies are formed, maybe wakes are formed, the turbulence level. Whenever I talk in terms of an urban area, well, it is much higher than in a rural area. Therefore, when these coefficients are determined, let us say the dispersion coefficient, let us say sigma x, sigma y, sigma z for a puff, and you have sigma y, sigma z for a steady release. It is not expected that in an open area like a village, the same thing should be applicable as for a city, and therefore, you have separate ones for urban area, you have separate plots for rural area, and not only are there plots available which we use, these are available in any standard book on atmospheric dispersion, And one of the good books on this is by Arya. You have these expressions available for urban areas, rural areas, for maybe a puff, for a steady release, and this is how it is. And let me get back to the slide now. And therefore, you have A unstable, Y, you have sigma Y, and what is going to happen as the puff or the steady release keeps increasing in distance? Well, it keeps initially it has a small dispersion coefficient, and thereafter it diffuses, comes over here, the value of sigma increases, it goes still further, the sigma value increases, and this is how the standard deviation or the dispersion coefficient changes. And these are all measured for different conditions of the atmosphere: stable atmosphere, unstable atmosphere, different degrees of unstable and stable atmospheres. So also sigma z is measured. I did this on the board, and again you have the value of sigma z changing with respect to the direction along which the steady release propagates. And as I told you, in addition to having plots, you also have maybe dispersion coefficients for continuous release in villages, rural areas, open surroundings. Well, it is given in terms of x, which is the downwind distance, for different values of atmospheric stability, which I just now said is A, B, C, D, E and F. Well, F is most stable, A is most unstable, and these are the coefficients. And immediately you see for the value of most stable, well, the value of sigma y and sigma z are very much greater than if it is stable. That means in a stable environment, the diffusion is very much less, and therefore similarly you have for the value for urban. Earlier in the last slide I showed it for villages, maybe for towns and cities, because you have blockages of buildings and enhanced turbulence. Well, atmospheric stability or the values of dispersion coefficients at different conditions of atmospheric stability. Here you have a condition between A and B, between E and F, because what is happening is, B also in an urban setting makes it more turbulent, and therefore the coefficients are stipulated between A and B, that is for both A and B is there for E and F, this is the value. Of course, different authors give different estimates depending on the type of experiments they use, and this is how we estimate. Now, the last point which I want to cover in this release is, we talked in terms of a puff being released in a medium in which there is no wind. Now, supposing I release q kg at time t is equal to 0 and you have a wind direction. Therefore, what is it I have? I am talking of my release with respect to the wind. Therefore, in the frame of reference of the wind, my x direction is x minus ut, and therefore, I just modify x. You recall when we had a puff, you had q divided by 2 pi 3 by 2 sigma x sigma y sigma z exponential of minus half into x squared by sigma x squared plus y squared by sigma y squared. This should have been, yes, I have taken the minus sign over here, I have taken the minus sign, therefore z by sigma z squared, the 2 sign is also taken out, and now instead of x in the frame of reference of the wind, I have x minus ut square, and therefore my dispersion coefficient at x corresponding to x minus ut, y, z and time t is given by this particular relation. Well, you can use this, and as I said, for a puff, well, normally sigma x is equal to sigma y, A most unstable condition, F the most stable condition, dispersion coefficient along x and y, which is nothing but standard deviation. Similarly, sigma z for condition most unstable, most condition, we have a series of lines which are all available to us. Therefore, this is all about atmospheric dispersion, but the problem which we have considered so far is, we considered only the case of a neutral gas. That means the gas which comes out is same, the molecular mass is same as the molecular mass of air. But supposing I have hydrogen, which is a very highly buoyant gas, low density, and let us say from the chimney it is pushed out. Therefore, what is going to happen? It is pushed out a distance from the height of the chimney or height of the release to a larger height depending on its buoyancy and also the initial momentum. Therefore, in such problems, it is necessary for us to be able to precisely calculate the height at which a neutral gas, namely diluted gas of the buoyant gas and air, is being formed, which thereafter I can use the regular formula for dispersion. But to be able to do that, we define something like a Froude number, and Froude number is something like the density effects, that is the weight of the gas, divided by buoyancy effects, we call it as densimetric Froude number, and we estimate that when I talk in terms of ZH, if I have a Froude number, if I have the height of the release given by the diameter of my particular release is equal to 1.1 Froude number, well, it is dominated by momentum. If ZH is greater than around 5.6, it is dominated by the particular buoyancy, and we can estimate this particular height from this height. Well, the spillage takes place after some time. Well, we want to form a neutral gas, that means the gas does not have any buoyancy left in it, it is a mixture of air and the small amount of hydrogen which then diffuses forward. Well, this is about diffusion, but one point I want to make before we try to solve a few problems, and whenever we solve problems we understand the equations better and we understand the theory better. We must remember, whenever we are talking of this, we always talked in terms of wind, the cloud cover. The cloud cover, we say insulation is the radiation which comes on it. Maybe if I have cloud, the insulation on the ground is moderate, and we categorize the entire atmosphere in terms of A, B, C, D and E, and also a very stable condition F, and this is how we did the problem. Therefore, we will do some problems in which we will be able to specify, given the question whether it is a winter day or a winter night or a summer day, hot summer day, we will be able to find out these coefficients and do the problem. But we must also remember there are some limitations in this. The limitation is, we are talking of, for a steady heat release, we stipulate the direction along the wind, which means the problem is not very steady. The wind direction is always not a constant. You go and stand outside, sometimes the wind is blowing, sometimes the wind is not blowing, suddenly the wind changes in direction. Therefore, since we do the problem along a wind direction which we assume to be constant, well, we are prone to making mistakes. We also assume that the wind speed is a constant, which may not be the case, because the wind speed, you have gusts, you have turbulence, you cannot have constant turbulence in the wind speed, therefore it is subject to errors. We also presume that as the plume is moving out, let's go back and look at this particular issue. As the plume from a steady release is moving out, we said, well, the mass of plume at this particular section is same as mass of plume at this section. That means the mass flow rate of the plume remains constant, which need not be the case, because we will have, because of rains, there is some washout of some substances, because of chemical reactions it gets consumed, these are not accounted for. In addition, even though we talk in terms of dispersion coefficients for, let us say, urban surroundings and rural surroundings, well, the wakes, it should have been wakes, ADs are not adequately modeled. Therefore, you do have a host of limitations, but we must remember the different aspects of atmosphere are included in this particular study on atmospheric dispersion. And therefore, having said that, let us quickly do one or two problems such that we understand the theory a bit better. Let us start with a small problem, and the problem what I consider is a problem involving a puff, a problem involving a steady heat release. Let us consider this problem of a puff. Let us say half kg of ethane is released at ground level. This is my ground. A half kg is released on the ground as a puff. Now, the wind speed given to me is 2 meters per second. It is also told that the release happens on a very hot summer afternoon. When I say summer afternoon, maybe it is almost midday, the sun is shining almost vertically above the particular place where the release is happening, and there is no cloud cover at all, it is a clear sky. Since it is a very hot summer afternoon and you have the vertical insulation available to me, well, the condition of atmosphere on that day is going to be A. Now, the problem which I am asked is, when this half kg of ethane is spilled over or is released as a puff, I want to calculate the concentration at a distance 50 meters away. Here at 0 time I have half kg. I want to calculate when this particular spill reaches here due to the wind velocity of 2 meters per second, what is the value of the concentration C, or let us say the value of chi in kilograms per meter cube. Therefore, we immediately go back to our tables, and if I go back to this table, I look at the puff tables for sigma y, sigma x is equal to sigma y, sigma z. This is also known as Pascal-Guilford tables for dispersion coefficients, and the values given are, if I look at the tables, I have sigma x is equal to sigma y is equal to, along the wind direction, 0.18 into x to the power 0.92 meters, where x is in meters, and sigma z is given as 0.60 into x to the power 0.75 meters. This is for the condition, atmospheric condition A, and this is the condition of atmosphere existing at that particular time. Therefore, now I substitute the value. Well, the wind speed is equal to 2 meters per second, and if you go back and see 2 meters per second on a sunny afternoon, let's do that. Let's get back to the slide and see what is the condition what we have. Well, surface wind is less than 2 meters per second. You have strong insulation, that is the condition is A only, and we said there is no cloud, there is A. Therefore, for A, these are these particular values. The wind velocity is 2 meters per second, the wind is carrying it, the distance I am talking in terms of 50, therefore, the time taken for the spill to reach me is equal to 50 divided by wind velocity is equal to 25 seconds. Therefore, I am interested in the concentration at a distance 50 meters away over the surface of the ground, that means along the wind direction, that means y is equal to 0, z is equal to 0 on the surface of the ground at a time 25 seconds away, and this I can write it as, I go back to my equation, we had the equation q divided by, I had 2 to the power 3 by 2, that is in 2 to the power 3 by 2, that is 2 under root 2 pi cube corresponding to sigma x, sigma y, sigma z, pi to the power 3 by 2, sigma x, sigma y, sigma z, into I have exponential of, we had the term x minus ut whole squared by 2 sigma x square, and I have over here, let me write the other terms. I have minus y square divided by 2 sigma y square minus z square divided by 2 sigma into z square. You know, I find I am interested in the along the center line of the wind, y is equal to 0, this z square, z is equal to 0, why? That means exponential of this term is 1, exponential of this term is 1. I have x minus ut. Therefore, I am now referring to x with respect to ut. Ut is 25 into 250, this becomes also 0. Therefore, this term becomes 0, and therefore, at a distance, let us say of, we are talking of x minus ut, which is equal to 0. Essentially, this corresponds to 50 meters into 0 at 25 seconds is therefore equal to the steady release. I said half kg is released divided by 2 to the power 3 by 2 into pi to the power 3 by 2 sigma x, sigma y, sigma z. When I look at the expression for sigma x, sigma y at x is equal to 50, I substitute here over here 50 meters. This expression comes out to be equal to 6.58 meters. This expression 0.60 x to the power 0.75 comes out to be equal to 11.28 meters. Therefore, I substitute the value, and I also know sigma x is equal to sigma y, and therefore, this becomes into 6.58 square into 11.28, and this becomes equal to if I calculate, it is 0.26 into 10 to the power minus 3 kilogram per meter cube. This is the concentration at a distance 50 meters away when the wind speed is 2 meters per second. This is the type of concentration we have. Now, supposing I wanted to do the same problem, let us say instead of specifying a very hot summer afternoon, I specify that maybe this release takes place on a very cold night, in which again I say, well, cloud is very small amount of cloud is available, and also the wind speed is very low at the same value of 2 meters per second. Well, very cold night, maybe temperature of the order of, let us say, minus 5 degrees centigrade or 0 degrees centigrade, and also this low wind speed. Well, this corresponds to the condition near to F, and let us now determine the value of the concentration for this very cold night. And what is it I do? I again find out the values of sigma x, sigma y and sigma z for the condition F. I go back and look at the table. For condition F, I have sigma x is equal to sigma y is given by 0.02 into x to the power 0.89, and sigma z is given by 0.05 into x to the power 0.62. For the condition of x is equal to 50 meters, I get this as equal to 0.7 meters, and for the condition of sigma z for x is equal to 50 meters, this gives me 0.54 meters. Therefore, immediately you see that for condition F, the dispersion coefficient is only 0.7 meters, whereas for the condition A, it was 6.58, that is around 1/10 of the magnitude. Similarly, here it is 0.54 meters. For condition A, it was 11.28, that is around 1/20th, and therefore, the concentration at 0, 0, 0, that means this corresponds to 50 meters, x minus ut is 0, corresponds to 25 seconds, is equal to again half divided by 2 to the power 3 by 2, pi to the power 3 by 2 into the value of sigma x, sigma y, sigma z. And now, you know, this if I calculate, if I put the value of, now I put half kg per second into these values, sigma x, sigma y is 0.7 square and 0.54, the particular concentration comes out to be equal to 0.475 kilogram per meter cube. Therefore, you immediately see when the condition of the atmosphere is cold, it is stable, I have a large concentration. When it is unstable, well, the gas sort of diffuses out very fast and I have a small value of concentration. But you know, this concentration in terms of kilogram per meter cube does not tell me whether this particular ethane concentration what I get is flammable or it is outside the limits of flammability, like we said L and F. And I can always consider this, I can always convert the concentration into volume of ethane, that is volume of fuel divided by volume of the mixture. And how do I do that? Well, let us just take this as an example. I have 0.475 kilograms. If I take ethane, I have C4 ethane, that is C2 H4, that is 24 plus 6, the molecular mass is 24 plus 6, that is 30 grams per mole. Therefore, when I talk in terms of 475 kilograms, I have to divide it by 0.03 kilograms per mole. This gives me the number of moles. In 1 mole of gas, I have something like 22.4 liters, that is 0.0224 meter cube. Well, this is the value in terms of volume of methane divided by volume of the mixture. And well, if I calculate this out, the value comes out to be something like 0.36, or rather 36% volume of methane divided by the volume of the mixture, and if I calculate this value, well, it is a very small number equal to something like 0.0194 percentage volume of methane in the volume of the gas. Well, this is clearly not flammable, but this is something which is somewhat even fuel rich, and that means it will get into a flame, or rather this could explode provided little more dispersion takes place. Well, this is the way we calculate. In the next class, what I do is I will take 2 more model problems, because we must know how to solve these problems. Maybe I will take the case of steady heat release, solve a problem, and then we go into quantification of damages. Well, thank you.